B Part 7, Tensor Algebra, for physics and classical mechanics and electromagnetism. Now, Lecture 3, multilinear map of 0-2 tensor, okay? In this case, this is a particular case of the previous lecture which we derived for 0s, okay? Now it's 0-2. Let's develop in detail the tensor T02 and a bilinear map on the tangent space TPM. You see, the tangent space is the domain. I'll give a similar example. Suppose in calculus you have y function of x. X is the domain. So, and y is the image or the codomain. So this red one is the domain, the tangent space. The bilinear map, this x on this domain here, which is TPM, the blue one. The setting, M be a smooth manifold of dimension n. TPM be a tangent space at P. Again, I insist and emphasize this is the domain. So this is the cotangent space, a space of one form of P, at P. Now recall, elements of the tangent space are vector. Elements of the cotangent space are covector. You see, this is a linear functional on vector. You see, this here shows clearly about the manifold. This is a real, okay? This is a point P. This is phi of 0 with a label xi at P. Then the green one is the fantasy. This is a space with we can map, okay, back gamma 1 from the green one to the point P. Attention, point Q coincides with point P, you see, but we gave an example just showing outside, but actually this grid belongs to the point P. Q it coincides with point P. You see, that's what we already have been done when we talk about manifold M. This is a tangent space, this is a cotangent space, you see? And this region here with a chart, U, Xi. Xi, again, I insist, is a label, okay? So, let's continue here. Definition of 0-2 tensor T. This definition is at P belongs to M. And a bilinear map on the tangent space TPM. Now again, this is red mark, which means that it is the domain. So the bilinear map T, the blue one, this is the domain, okay, acts on the domain. This leads to a real number, okay, by definition of a tensor. Now, T, I can write, is TPM, product, tensor product, T asterisk TPM. So, in terms of local coordinates, you see, this is the blue one, Tij, there's a basis, okay? The basis, this belongs to the cotangent space. This over here, okay, this also belongs to the cotangent space. Remember, Tij is covariant, okay, because you have lower indices, Ij. Now this map, bilinear map, and this is the domain. You see, this acts on the domain. So the domain is xm, yn. This is the basis of the tangent space. You see, tangent vector space. You see, you map this, and this leads to R as we see here. Now, recall that the inner product, you see, this is a two-form. This is the basis, okay, the covariant basis, okay. This equation here, this tensor product here, this is the basis for the two-form. This is the basis of the tangent space, okay. Now, because we are working with a two, this is two tensor products here, okay. Likewise, this is called Cartesian product. This is time over there. So let's show that this leads to the scalar R, which is the definition of a tensor. Now, again, coming this relation here, this is the inner product, okay? This inner product over here is dxy reach partial of xm, and dxj reach the partial of xn. You see, I just wrote over here. I separated, okay? So dxi partial xm, dxj partial xn. So this, by definition, this is here, is delta im, and this one is delta jn. You see, I'm writing over here. Now, then this here, we act on this xm, yn. You just follow here. So delta, the property of delta im, okay, this over here, this delta im applied to xm, will be xi, okay? And likewise, delta jn, you can apply to yn, will be yj. I just write over here. So this I have xi, yj, lower index. This is xi, yj. You see only dummy indices over here, which is a scalar. This is a codomain. So this is a local action. The blue one, you see, comes from the tensor T, the blue one. This xi, xj, okay? This belongs to the scalar R, okay, with the definition of a tensor. So that's it. That one application of S is equal to. Next lecture, lecture 4, I will present a numerical example. See, just showing this development.